everyone. Can those people in the way back hear me? How's the sound? Not? We could be louder. Okay. Mary, could we turn it up just a little bit? We thought we had it arranged, but it makes a difference when the room fills with people too. So we'll, is that better? That better? Okay, great. I want to welcome everyone once again to the Tony Woiak Winter History Festival. It's the 13th year already, and that's kind of amazing to think about. It started as just a winter festival because we thought people needed something to do in the winter. And then it became popular enough, and we kept coming up with good ideas for programs. And so now it's been winter and summer for some time, 4 programs in each season. So thank you for all of you who have been with us from the start and keep coming back. We appreciate that. And I've spoken with a few people tonight already who this is maybe their first Tony Woiak Festival. So welcome to you. We want to thank the Harbor Table for hosting us and doing all the setup for us and having the bartender here, so we've got somebody that can offer refreshments to us. So I think we can applaud for that. It's a very, very nice place to be, really. And now that we've got our sound system and visual hopefully set up, it's better for the audience. I think we've solved some of our problems. But please, we're still anxious to have your feedback on that. And so let us know if you can think of something we can do to make it better. We have 2 more programs in this winter festival. And so come back in 2 weeks and see what comes next. It'll be advertised. We want to thank also we got a grant this year from the Washburn Community Education Foundation, and that was what helped us afford some of these upgrades in the AV system. And so we really appreciate that organization for the money they raise for local groups that have an educational purpose. Also, we've got, well, let's see, I don't want to miss anything. That's it. Tonight we have the honor of welcoming Dr. Tom Fitz, Professor of Geoscience at Northland College. And I just think geoscience is a cool term. It's like, oh boy, geoscience, sounds great. And I am excited to hear, looking forward to learning about, our mission is to tell our stories. And this is a story that goes way back. So we're going to learn about the story of the land before any of our humanity was on it. And so welcome to Tom. Last time we had questions during the program. We're going to try to hold questions until the end tonight and see if that helps us with timing. So if you've got a question for Tom, don't forget about it. We'll leave time at the end, and comments or questions will be saved. So please help me welcome Tom Fitz.
Okay, hello. Can you hear me okay?
Yep.
Yeah, thanks for coming. Okay, just a second here. Get this clicked on. I hope. Yeah. Okay, so not last week, 2 weeks ago, we were here and we heard about the Washburn Iron Works, and Cole Pearson started out by asking us what we had for breakfast and perhaps how that breakfast was cooked. And then he went on to tell us about the cast iron fry pans and the importance of iron in our society. And so what I'm going to start with tonight is something similar. It's not going. Sometimes it falls asleep. Okay, so I'm going to ask you a similar question, and that is, hang on just a sec, I think that might be a little, is that good? Yeah, okay. I'm going to ask you a similar question, and that is, why are you here? Why are you in the Chequamegon region? Okay, and why is the Chequamegon Bay here? And why is Lake Superior here? Okay, and all of those probably have to do at least somewhat with geology. So that's what we're going to be talking about tonight. Okay, so the geologic story really has 3 parts, and we're going to proceed through them. The first part it has to do with the ancient rock underneath. Okay, so we're going to tell the bedrock story. It does go back billions of years. We're going to start at the very beginning, 4.5 billion years ago. All right, and then there are the glacial age sediments sitting on top of the rock, which takes us back about 12,000 years. Okay, and then we have the more recent post-glacial, since the end of glaciation, and the development of the soils and the landscape around us. Okay, and then what we're going to do is we're going to talk about why all of that matters to us today. Okay, so the plan is, first we're going to talk about the ancient geologic story, all right, it goes way back, and then the glacial history, and then we're going to talk about after the glaciers, what has happened after the glaciers on the land and in the lake, and then we're going to tell the human story and how we have interacted with all of that, right, and then some concluding thoughts about the whole big picture. Okay, so we go back to the very beginning, 4.5 billion years ago, and the Earth formed from a whole bunch of meteorites that came crashing in together. It was a very hot beginning, right? And first thing that happened was that the whole planet was molten, right? Everything was molten, and slowly but surely, over a few 100 million years, the crust of the Earth formed. Okay, and so the oldest rocks on Earth date from about that time, all right, about just over 4 billion years, all right, and those rocks are the original crust, the first stuff to be preserved on Earth. We don't have exactly the oldest stuff, but we have some of the oldest stuff in the world right here. Okay, here's the geologic time scale, all right, and this goes back to 4.6 billion years ago, right, and these are the geologic time periods, and I'm going to be referring to this at our different episodes in the geologic history. Okay, so the oldest rocks are down here from about 3.8 to 4 billion years old. Okay, we don't have quite the oldest, but we do have some really old ones exposed in the Pinocchio Range in Minnesota and in Michigan, sort of on the edges of the Lake Superior Basin. Okay, and they all look like this. This is what's called a greenstone, right? It's a pillowed greenstone. And what these structures are, those are where lava came out on the ocean floor. This was before there were any continents, right? So there were no continents, everything was ocean floor, and it was basically just this basalt coming out and forming these pillows, and the pillows form when the hot lava interacts with cold seawater, right? So that's the original crust for nearly 4 billion years old. Our next episode, right, this is the thing about the geologic time scale, is that there are time periods that are fairly well represented, but then we have these big gaps in time where there's no rock that tells us what happened, right? And the further back you go, the more fragmentary this story is, right? So we're going to go next, we're going to skip 2 billion years, okay? And we're going to come to the next youngest rock in this region. It represents a time when the Earth's chemistry of the oceans and atmosphere was changing pretty dramatically. All right, and this is called the Great Oxygenation Event. Right, it's an event, a geologic event that lasted several 100 million years. Okay, nevertheless, the Earth would change during that time period, during the Great Oxygenation Event, and it all had to do with photosynthesis. The first photosynthesis on a large scale that released free oxygen into the atmosphere. Okay, and oxygen is very reactive. And if it isn't constantly being produced by photosynthesis, then we wouldn't have any. And so what happened when that first oxygen came out of photosynthesis in the shallow oceans, it quickly reacted with iron, all right, iron in the ocean. And it was deposited onto the ocean floor. There was a reaction between the oxygen that was being released and the iron. The oceans were very rich in iron at that time. And there was a deposition, this chemical process that deposited lots and lots of iron on the ocean floors 2 billion years ago. So basically, the world's oceans were cleansed of their iron and it was deposited on the ocean floor. And that is the iron that we now use in our society that Washburn Iron Works is melting and turning into the fry pans that we use. Okay, so that's the first part of the story. Okay, and they are spectacularly beautiful rocks. All right, you've probably seen them before. I'm going to show you a few pebbles later. Okay, but they're distinctive. What is in this rock The gray bands are the iron oxide, and the red bands are jasper, okay, which is quartz with iron in it. So they're really spectacular, beautiful rocks. The more iron oxide there is, the richer the deposit is. Okay, so this one over in Michigan is not that rich of a deposit, but they're called banded iron formations. Okay, so here we are, okay, in Chequamegon Bay, right there in Washburn, right, and this is the bedrock geologic map of the area, right, and this is the Chequamegon Range right there, and that's the iron formation. Okay, it's called the Ironwood Iron Formation. It's this belt that comes along here like this, right, and that's where all the iron is, and we're going to come back to that and talk about iron mining, okay. All of the rocks have been tipped up on their edge, okay, so when you go from down here near Mellon up towards Chequamegon Bay, you're going across basically this great big book of geologic history that's been turned on its side. So it's a great place to study geologic history, right? And up here where we are, these are the youngest rocks in this area. Okay, they're still pretty old, 1 billion years old, and it's all sandstone. So everything here in the yellow and in the brown is the sandstone that we know from the shorelines here and out in the Apostle Islands. Okay, so the next big event that we're going to talk about, okay, those are the iron formations at 2 billion years ago. So we have the old rocks down here, now we have the iron formations at 2 billion years ago. Then we take another jump of 1 billion years, nearly, okay, and we come to 1.1 billion years ago. The last really big bedrock geologic event in this area was 1 billion years ago. And what happened was, at that time, what was North America, which was really pretty different than it is today, okay, actually started to split open. We call it the mid-continent rift, right? And it started to split open in the middle, and it started to create an ocean basin like this diagram shows. So the mid-continent rift went about this far. It did not open up into a great big ocean basin. And because what happened was that it opened up for about 20 million years, and then it stopped and basically filled in with sandstone, the sandstones that are all around us, and then it got tectonically crushed like this, okay? So it didn't open up into an ocean basin. But in that 20 million year period that the mid-continent rift was erupting, it was absolutely huge amount of volcanic activity. Right, one of the biggest, like the 4th largest volcanic province in Earth history that we know of. Okay, so it's like 3 million cubic kilometers. Think about what a cubic kilometer of lava is. 3 million cubic kilometers of lava came out of Earth's surface, okay, that is now represented by all these lava flows in the western Lake Superior Basin. Okay, so here it is. This is a map of the mid-continent rift, how it looks today. Okay, the green, all of the green in here are the lava flows and the volcanic plumbing system underneath it. And then the yellow are the sandstones that we're going to talk about next. Okay, here's some basalt. Okay, this is actually over near Duluth. You can see Duluth in the background. And you see these ridges on the basalt right there. Basalt is the black volcanic rock, right, that comes out of Hawaii and Iceland right now. Okay. In fact, this was actually kind of a similar setting to what Iceland is today. Okay, so, whoops, I'm going the wrong way. Okay, so you can see that this was crumpling lava. And that was the surface of a lava flow that was actually crumpling as the lava was flowing underneath it. Okay, and there's really kind of spectacular volcanic geology in the North Shore of Minnesota, also in the Keweenaw Peninsula, and down in the Pinocchis as well, at Copper Falls State Park. This same stuff is exposed at Copper Falls State Park. Okay, this is up near Grand Marais, Minnesota, and you can see each one of these is a lava flow. Okay, so it's all been tipped a little bit, but just like 5 miles of lava stacked up on top of each other. Okay, and then what happened was that after the volcanoes died, all right, the Great Big Rift Valley was filled in with sandstone, with sand that was turned into sandstone. Okay, and that is the sandstones that we know and love all around us here. Okay, I took this picture out at the sea caves near Cornucopia, okay, a few years ago, last time it flowed over. Yeah, beautiful sandstones. It's called the Bayfield Group. The Great Bayfield Group sandstone is several miles thick of sandstone, and it's exposed right over here as well. Okay, and then, as I mentioned, there was this great big tectonic squeeze, right, shortly after the sandstones were deposited, and the whole thing got folded up into this great big canoe shape. So basically, the western part of Lake Superior is this great big canoe that has these basalts on the edges in Minnesota, and then on the Keweenaw Peninsula with sandstone in the middle. Okay, and that's going to play an important role when you get to glaciation next. Okay, and then we have the glacial story. Okay, so we jump another billion years, okay, and we come to this scene right here would be about 20,000 years ago, the last glacial maximum, what we call that, the last glacial maximum. So the last time ice came into Wisconsin about 30,000 years ago, right, and advanced to this stage right about here, right, and we had probably had about a mile of ice over what is now Chequamegon Bay 20,000 years ago, right? And then that was about the last glacial maximum, and then it melted back, and the edge of it got to here about 13,000 years ago. And the ice sort of fluctuated a little bit, the edge of the ice, for a little while before it finally melted out like 12,000 years ago. Okay, so here's the glacial story, okay? Glaciation. So the way to think about glaciation, we went from talking about billions of years to talking about thousands of years. And to put it into perspective, right, we think about glaciation almost like it happened like as we were coming together here this evening, right, like half an hour ago. Half an hour ago the glaciers left, and now here we are in this glacial landscape, right? I mean, that's kind of the way you think about it, whereas, the mid-continent rift was like, a long time ago, right? So glaciation, just very recent. The first thing that happens when you get a mile of ice is that it scrapes anything that's sediment, everything that's soft gets scraped away, right? Because the glaciers are very good at scraping and grinding down to the hard bedrock, right? And what it does is it puts these scratches on there. Okay, so these are called glacial striations, and you can tell which way the ice was going, right? Scouring the land. And the harder rocks, the harder basalt lava flows, those ones were more resistant to that abrasion, and they didn't erode down as far. The sandstones sitting in the middle, okay, much softer, right, much more erodible. I mean, these sandstones, you rub your hand on them and you can feel like the sand grains coming off, right? So a glacier that's a mile thick goes over those and it eroded it very deeply, okay? And that is why Lake Superior is here, okay? Because, and this happened repeatedly, the ice came along and scraped it out and pushed it all down into southern Minnesota, okay? So, and spread it around. So that's why we have the lake, all right? So what we have is the hard lava flows here on the Keweenaw Peninsula, Isle Royale, and then also on the north shore of Minnesota. The sandstones in the middle, they've been eroded down lower, okay? And then when the glacier melts, all right, it doesn't, when we say glacial retreat, that means the edge of the ice never actually backs up, right? It basically just stops. And then, because the climate is warming up, and it just melts in place and deposits everything that it had, right? Just lets it down. And that is called glacial till, right? And we have a lot of glacial till in the hills up here, especially to the south, okay? Glacial till, and it's everything the glacier was carrying. It doesn't sort it out at all. It's like all the clay, the silt, the sand, the boulders all get dropped in together, okay? And that's going to be important because we're going to be thinking about what kind of soil that makes next, all right? So then we'll go back to, this is maybe 13, not quite 13,000, yeah, about 13,000 years ago, okay? And the ice had melted back. Here we are in Chequamegon Bay. There's Washburn right there, okay? And Duluth is over there. There was the superior lobe of ice, and then what's called the Chippewa lobe right there. And you can see that the center of the Bayfield Peninsula was exposed. The ice melted off of that area first. And so what was happening was the glacial meltwater coming in. When a glacier melts, there's a lot of water, okay? And it comes flushing out of the glacier, carrying a lot of sand with it. And it was flushing sand out of the glacier into what is now the middle of the Bayfield Peninsula for a long period of time, just flushing the sand out there, right? And then what we get is this sand country, okay? So you drive up above Washburn and Bayfield and get back there into the sand country, and it's just, as you guys, this is a map from the Wisconsin Geological Survey. look at this. This is the depth. I mean, it's 500 feet of sand. The Bayfield Peninsula is basically a 500-foot deep pile of sand that was flushed out of glaciers from each side, all right, which is pretty cool. All right, and then you can see that extends down here. It's a great big long stretch. You go down near Barnes, you know, the sand just continues. And it's distinctive soils and distinctive ecosystems as well. Okay, so then you go to about 11,000 years ago, and the ice was melting further back. It left this area for the last time, all right, but it wasn't completely gone from the Lake Superior region. So that means that what happened, there was a great big lake here in the western part of the Lake Superior Basin that we call Glacial Lake Duluth. Okay, in Glacial Lake Duluth, the shoreline was, well, the outlet was the St. Croix River, okay, at Brule. All right, so 500 feet above it right now, okay, so that means that there's a shoreline up there 500 feet above us of Glacial Lake Duluth, okay. Here it is. This is my colleague Dave made this map from U.S. Geological Survey data. Okay, and here you can see this is where the shoreline was. These were the original Apostle Islands. Okay, and here's the outlet to the St. Croix River and down into the Mississippi. So the lake at that time was draining into the Mississippi rather than into the St. Lawrence. All right, right. And now what you notice is that this whole region was underwater. Okay, under 500 feet of water. All right, so then what happened was all those glacial deposits up there, right, were being eroded at that time, and there was erosion, transportation, and deposition, and what was deposited was the clay, right? So, as you know, we have a lot of clay in this area, all right, and there's a pretty distinctive shoreline up there 500 feet above us, okay, Mount Valhalla, all right, the parking lot of Mount St. Valhalla, in the ski area there, that little flat plateau there, that is the Glacial Lake Duluth Beach. Okay, so if you're below that, chances are you're in clay, all right, and if you're above that, chances are you're in sand. All right, so that was up there. The clay was being deposited. Okay, and there it is. You probably recognize that, right? Sticky, clay, all right? Yeah, kind of messy stuff. You love it and you hate it. It's probably stuck on your boots right now, on your dog's paws, right? So this is the glacial map of this area from the Wisconsin Geological Survey. The clay plain, what we call the clay plain, is shown in this sort of blue-green color, right? And then the shoreline of Glacial Lake Duluth is right there, okay? And in some places you can actually see there are beach deposits. Some places where it's really nicely preserved. You can see it's like, wow, it's a step in the landscape, it's a sand strip, you know, it's got all the features that you expect of a beach that's now high and dry. Okay, and here we are down here on the clay plain. Okay, yeah, here we are, right there. Okay, and this is really important change right here along the beaches, because this is all sand up here. This is mostly clay. We'll get it's not all clay, but it's mostly clay down here. And then the green, you see the green deposits in here, that's where there's actually the glacial till that was actually let down. Okay, so we had really 3 different types of depositional environments at the end of glaciation. Okay, there was the till that was being deposited directly, we had the outwash that is all sand, and then we had the clay that was being deposited on the bottom. Okay, so 3 different geologic environments, 3 different types of deposits, and today, 3 really pretty different types of soils. Okay. So this is my students on one of the beaches. This was actually down at High Bridge, okay, where the beach is beautifully exposed on Bass Lake Road, right? But this, you could do the same thing up there at Mount Valhalla. Okay, and so here's the beach. That's where the waves were breaking. Up above this is all the older deposits, and to the right, it's all the clay. Okay, so it's a distinctive step in the landscape. It's also a distinctive change in the glacial geologic materials, thus in the soils, and as we'll see, also in the ecosystems and the way the water flows off the land. So it controls so much. Okay. It's not the whole story though, okay? So if you've done some digging around here, if you have a garden, you know, you probably have some clay, but not necessarily, okay? Because what happened is that when the lake was, when the ice was melting out of the lake basin, all right, the outlet found progressively lower steps, right? So it found these other outlets that were lower. So when the lake level came down, it didn't fall all at once. It came down in a series of steps over probably several hundred, if not 1,000 years. Okay, so it's coming down like this, makes a little bit of a shoreline. So here's the glacial Lake Duluth shoreline that is really distinctive, right? And this is the next one down, and then it paused, and made another little shoreline. Okay, so these little shorelines are creating like little sand strips, within what is mostly clay in that area. All right, and then it comes down again, and then it actually the lake level fell to lower than it is today, like 375 feet lower than today in this area. Okay, and it's fascinating because we're starting to get some more data about the bottom of Lake Superior, and out between the Apostle Islands, there are actually old riverbeds. Okay, and you can see them in some of the data that the United States Geological Survey is getting. Right, so it's like, wow, this lake level fell, and there were rivers out there, and then the lake level came back up to about where it is now, about 2,000 years ago. Okay, so it's been about 2,000 years that the lake level has been steady enough that it's been able to carve out these sea caves and create all of the beach features that we now see, that we know as the coastal geology of this area today. Okay, so about 2,000 years. Okay, so I don't know if you've heard of LIDAR, but LIDAR is a new mapping technique where we can see Earth's surface we can see the topography really clearly, right? And LIDAR imaging is really kind of changing our view, giving us a lot more detail about the topography. And so what we're going to do is we're going to zoom in. Here's Mount Ashway, okay, and there's the ski area right there. All right, we're going to zoom in a little bit, all right, and here it is. This is the LIDAR image. And you can see this is the glacial Lake Duluth shoreline right there. And you can see how distinctively different topography is above the glacial Lake Duluth shoreline. That's the older topography that was, the rivers flushing sediment out of the glaciers, okay? And then that was the glacial Lake Duluth shoreline, and then you can see these steps. Each one of those is a place where the lake level came down and paused and made a little beach, and came down and paused and made a little beach, just like that. Right? So these little beaches are superimposed on that clay plain, like that. Just pretty amazing. So you can see the topography is different here, and then you can also see how this is much more subdued topography, and that's because the waves were working on it. As the lake level fell down, the waves were working, kind of smoothing the whole thing out. All right? And then also, something that's really interesting to notice is, of course, that this is mostly sand, right, because it's the older deposit. And then this is clay, and where the rivers begin. You take a look at this, and the rivers begin just below the glacial Lake Duluth shoreline, right, there and there. So it's like it's like the topography is really different. And when the water falls on this surface, does it hit sand or does it hit clay? It behaves very differently. Okay. Okay, so then we've got this, the glaciers, came, they scraped, they melted, they made these deposits, all right, and then what happened is gradually life returns, okay? And so after the glaciers, the first thing that happens, we have all this glacial sediment there underneath it all, and then it reacts with the water, and then one of the first things that happens is we get vegetation. Okay, and as soon as you get organic material landing on your surface and decomposing, we have soil forming processes. Okay, so soils start to form, and so what we've had is we've had 10,000, 12,000 years of soil forming processes taking place here, and this older glacial material is being transformed in the upper part into soil. And soil is just beautiful stuff because it supports life. All right. It is partly geological, it is partly biological, it is partly atmosphere, it is partly hydrosphere. And you think about all of the resources that come together in soil. All right. It's just beautiful stuff because of the wealth of resources that are available to it. Okay. And in this area, we have basically 2 or 3 different types of soils. Okay, we have the sandy ones and the till ones, and then we have the clay ones. All right, and why this matters, of course, is how water moves through them, as I mentioned. Okay, I took this picture along the Brule River. Okay, and you can see it's kind of a till soil. all right? And what you can see, it had been really dry. This was a few summers ago. We had just kind of a dry spell, and hadn't rained in like 2 or 3 hot weeks, you know. And then I was on a canoe trip with a friend, and it rained hard the night before. One of those like life-giving rains, you know, just like, ah, oh, thank you, right? And then the next day we're paddling, and you can see this, what's called the wetting front as it progressed down through the soils, right? And so it would be really different. This is kind of a till soil, it's a loamy soil, right? So it advances at, you know, moderate rate, right? And then that's very different than a sandy soil, where the water can go right through it and isn't retained very well. Or a clay soil, where it just runs off, right? So really pretty different stuff. So what we've got is we've got the sand and gravel, we've got the clay, right? And we've got very different soil properties and very different hydrology as well. Okay, so if you're down here in the clay plain, right, you see this kind of thing, right? The water is sitting on the landscape, right? And if you think in the springtime, you know, in some of these places, you know, it's kind of undulating topography, it's just wet for a long period of time. Okay, oops. Okay, so you go up into the middle of the Bayfield Peninsula, right? This is out on 236. You can see the really sandy soils. You get the pine barrens out there because the soils are so droughty. Right, in the middle of summer, hasn't rained in a long time, there's basically no water. All right, so that's where we get the jack pine and the red pine and the scrubby oaks, the hills oaks. Okay, and then you go to, this is in the Pinocchio Range, right? We've got the till soils, the loamy texture soils, all right, and which hold water pretty well. And you get these great big sugar maple forests, sugar maples and hemlocks. Right, really pretty, very different soil conditions. Okay. The other thing that has happened is that since the lake level has stabilized at about where it is now for about 2,000 years, what has happened is that the waves of Lake Superior have done a lot of sculpting. All right, so there's a lot of sand sitting around, all right, at the end of glaciation, and so when waves come down the beach, they move up the beach that way, and then they wash back like that, and they come up the beach that way, and they wash down like this, and you do this for 2,000 years, and you get a lot of what we should call longshore transport, right? And the beach is basically a river of sand, right? And it's being transported. It's not always going the same direction, but most beaches, it's got a dominant direction that it's going. It's going to go this way, and then a couple days it'll come back, and then this, and then like this, and it gets transported all the way along, all right? And so we go to this, and we've got so much sand around here, and the waves constantly working. What it has done, it has created these great big sand spits, okay? And this is Long Island, okay? And Long Island, of course, is a great big feature that basically closes off Chequamegon Bay, right? So we have the great big waves out here of Lake Superior, which are very dangerous at times, and then we have this beautiful protected area that is the bay. That may be one of the reasons we're here. Okay, into this environment that we have set up come humans. Okay, and probably not too long after the glaciers exited the land, there were humans coming into this area. Okay, so, but we go back to about 2,000 years ago, and we have this setting right in here. Okay, my former colleague Jim Meeker, Honorable Jim Meeker, took this photograph a long time ago. All right, and this is the Chequamegon Sloughs right here. There's Long Island. We're over about here right now. All right, and this is one of the largest wild rice beds in the world, okay, which is originally why people came here, right, for the food that grows on water. Okay, so that's the first thing that brought humans here, right, and so the harvesting of wild rice. And that's still important today, very important tradition, very important food source for Native Americans and for all of us, okay. Yeah, and the reason is because of the geology, right? Because of the sand spit sticking out there, protected it, made this area of shallow water. It's perfect for wild rice to grow, okay? Then in about 1850, okay, when Europeans were first coming into this area, they started sticking some magnets on the rock, right? And in some places, those beautiful banded iron formations have a lot of the mineral magnetite on them, and a magnet sticks right on there, and your compass doesn't point north. it was probably very easy to find these iron formations if you had a compass, if you had a magnet, right? About 1850. There it is, right there. This is this one doesn't have the red jasper in it, okay, but it's got the silvery colored mineral. There is all the magnetite, the iron oxide, and there's my magnet stuck right on the rock. There aren't a lot of places in the world where you can like stick a magnet right on a rock because it has so much iron in it. Okay, and it didn't take too long before iron mining was a big industry here. Okay, so it was about 1885 the first shipments of iron ore left this area. Okay, the mining was in ironwood all along the Pinocchio Range. Okay, and then into Michigan as well. Okay, so we had some really big mines. They were all underground mines. Okay, they were going after the higher grade stuff. All right, but played a very important role in the history of this area. All right, I'm going to show you some historical pictures here. They're almost all from Wisconsin Historical Society. I couldn't actually figure out where this one was taken. It's on someplace on Chequamegon Bay. It's one of the oldest ore docks out there. Okay, so the mining took place from like Ironwood, Michigan, over towards Mellon, Wisconsin, all right, and it all came here, okay, because of Chequamegon Bay. It was protected, all right. I like this one because this one's pretty old. This is the ore dock in Ashland, okay. Whoops, and you can see these ones still had sails on them. I don't know when that one was from, but that's pretty historic right there. Still sailing ships and shipping their ore out, right? At that time, there was ore. It's direct shipping ore. They're just digging it out of the earth, putting it on the ships, and sending it down to the lower lakes where it was turned into iron, steel. Okay. This is also interesting because this is the area just below Hotel Chequamegon, right? And you can see what they're doing here is they're filling in some of the old ravines. And unfortunately, what was filled in there was also not just the waste from the lumber mills, but also some of the coal tar sludge, which ended up being the Ashland Superfund site that we just recently finished cleaning up. Okay, so this is probably the beginning of that big mess right there. Okay, the iron ore was shipped out of Ashland from 1885 to 1965. Okay, so it's like there were about a dozen big docks there that were, unloading coal, loading iron ore, loading lumber. Okay, so it was a very busy place. Okay, so there were a lot of hungry people, right? And of course, the waters of Lake Superior, the big, beautiful, deep, cold waters of Lake Superior supplied a lot of fish. Okay, right. And of course, brownstone, which is the sandstone that we mentioned that filled in the rift. Okay, so brownstone industry was big and booming. This island, you probably know, it's like right down there, like a mile down the way. And it's interesting because on this side, I don't know if you can see it in this view, but on one of these sides, you can see a drill hole. All right, and I think that thing is that island is probably a remnant. I don't know this, but I don't know why else there'd be a drill hole there. A remnant from brownstone quarrying, right? And there's also a chain hanging off from one side as well. Okay, so big blocks of brownstone were lifted out of the right along the shoreline and then loaded onto ships. This is in Basswood Island, right? Loading the ships loading the brownstone right onto the ships. I love that one. There's geology playing a big role in the history of the region. Okay, and then also these beautiful, huge forests that we have. We've got some pretty nice soils, right? And we got 33 inches of rain per year, which is a nice setting to grow big forests. Okay, and of course the lumber operation supported all of this, right? So there was a building boom with brownstone and with lumber, and then also a lot of this was used in the ore docks and then in the mines as well. So there was a big demand for timber at that time. Okay, and of course Chequamegon Bay had big booms of logs on it, right? And there were active sawmills, some big ones here all the way up to Bayfield, right? Right on. That's from the Wisconsin Historical Society. That's the last log that came off one of the big sawmills around here. Okay, So, resources, the geological resources of this area played an important role in people coming here, and the resources that built up this society, and they continue to today. Right? We have these glacial deposits are pretty amazing for their resources, for the ag. Okay? In the United States, each one of us is responsible for the extraction of about 18 tons of earth material every year. About 10 tons of that is sand and gravel. Okay, sand and gravel for construction. So it's roads, it's buildings, it goes in concrete, all right, so a lot of it. And there are a lot of places in the world where there isn't adequate aggregate, all right, there isn't enough sand and gravel. And it's very expensive to move because it's so heavy, all right, so we don't export a lot from here because it's so heavy, but we do have an abundance of it, okay? And that was 6th Street in Ashland a few years ago, and you can see the sand, that's wells, you know what that is? That's Glacial Lake Duluth sand. And it's just amazing, these sand, like it's well-sorted, beautiful sand, all right, yeah. And then, of course, we have the beautiful shorelines, okay? And this is, I think, one of the most important resources we've had for a long time, and that is the beauty of this region, and the beautiful Lake Superior shoreline. Okay, that is on Sand Island. I took that picture last summer, okay? And people have been coming here to the Apostle Islands and to Chequamegon Bay for a long time, for recreation, for relaxation, and to connect with nature, okay, for a long time. Yeah, it has been well known, okay. This is one of my classes out on Stockton Island last fall, right, so beautiful place to come. People come from people come a long ways to go see those sea caves, and then, you know, if you were here the last time it froze over, I think that was 14-15. I think it froze over in 13-14 and 14-15. You could actually go out into those caves, you know, and it's like, back the first time I went, like in 2005 or something, it was like you just go out there and there's nobody around, right? And then in 2015, it was like, what, 250,000 people discovered the Apostle Island sea caves, right? It was pretty amazing. Okay, so I want to mention just a few beautiful things to think about here in thinking about our connection to this area and its geologic story. All right, whoops, and that, whoa. And that is the sand, okay? So we have a lot of sand here, and you walk down the beach, you pick up the sand, it's wonderful stuff, right? Some of the beaches here, between here and Washburn especially, I mean between here and Bayfield, just spectacular sand beaches, right? And think about the history of those sand grains, okay? Some of those things were probably in some of those really old rocks, nearly 3 billion year old rocks, right? And they were eroded out of those and they were deposited into the mid-continent rift as it was filling up, right? And then they were in that great big continent collision, right? And folded up into these forms, and then were in the sandstone for a billion years, and then the glacier came along and scraped them out, and then they were deposited along the shores of Glacial Lake Duluth, and now they've made their way down to the present shoreline of Lake Superior. Okay, so these 2 billion year old or 3 billion year old sand grains that each have this amazing story within them, all right? And they've just been sculpted. They've been pushed around by the waves, they've been pushed around by the dunes, that's on Stockton Island, okay? And to create these beautiful shorelines. And there they are, coming out of this. I took this picture just down the shoreline here, okay? And there it is, the sandstones, the crumbly sandstones like falling apart, right? And making the sand that we see all around us. Right, pretty cool. And then you'll see this on some of the beaches, right? I mean, you see this, not all a nice, pretty quartz sand. You also have these black sands, right? You've probably seen that. This is out, took this picture on the Apostles, and you see all the black sand right there? That's the mineral magnetite, right? Which is the iron oxide that was in the banded iron formations. So there are not a lot of places in the world where you go to a beach and you have, like, you pick it up. I think I got another picture here. You pick it up and you're holding black magnetite sand, okay? This stuff is really hard, really resistant to weathering as quartz is. So when you pick this up, you're picking up these grains that are, you know, probably 2 billion years old. They were eroded out of those banded iron formations, those beautiful banded iron formations. There's a microscopic view of it, right? So that's a 0.5 millimeter pencil lead, and that's quartz. And that's the magnetite right there. Beautiful black sand beaches. It's iron oxide. I did, while walking down the beach, I did a little beach art one time. I wondered what became of that, right? And then occasionally you'll pick up one of these pebbles, right? These beautiful red jasper pebbles, right? Telling the story from long ago, from the oxygenation, the first oxygenation of the earth that gave rise to abundant life. And then you find pebbles like this. This is a piece of basalt from the mid-continent rift. These right here, these bubbles, right, they were bubbles in the lava flow originally, gas bubbles, and those bubbles got filled in with different minerals, all right? A lot of different minerals filled those in. This one's quartz. You can see it's really hard and kind of making the end of that thing. This is a bunch of different minerals in that one. And one of the things that can fill it in is quartz, sequentially filling it in these bands, okay, of white quartz and red quartz, and those make the beautiful Lake Superior agates. All right, so those are kind of a legacy from the past as well. I just wanted to show you that picture. I took that one last summer paddling just north of here. All right, you can just see the reflection and the ripples on the bottom. So cool. Okay, so some conclusions about the past, all right, and leading up to today. All right. So it was the geologic history. It was the bedrock story, right? The bedrock story, like, laid down the rock, right? Created the atmosphere that we know that we can breathe, all right? Laid down these rocks that would end up being really important resources to us, all right? Then the glaciation sort of rearranged all of the sediment, scoured it out, made Lake Superior, all right? And created the setting in which then people arrived, all right? And then, I liked this one. I really like this one. I took this one. I think that was out on Devil's Island. Okay, ripples in the sandstone. Okay, and those ripples, you can see those ripples? Those are distinctively beach ripples. Okay, so those were created on a beach by waves 1 billion years ago. It was probably a small lake within the mid-continent rift as it was filling in 1 billion years ago. And then, you see, I took this picture recently, right along here, and you can see the same shape of the ripples. Okay, so it's like this geologic story is like many of the same things keep happening again and again and again. Okay, so that the processes of Earth continue. I want to end with a couple of thoughts here. Okay, I've had the honor really of being a professor at Northland College for 25 years, and I just totally love my job. I've loved learning about the geology of Xeri and sharing it with people. And I just want to end with a couple of thoughts of this. This is the Northland College logo, okay? And it shows Newton Bob and a student, right, cutting trees down to help heat buildings of the college. And the logo says, "A highway shall be there." And when I teach the freshman seminar every fall semester, the students go, "Why does the Northland College logo, the Northland College, the Environmental Liberal Arts College, have two people cutting a forest down as the logo, and it says a highway shall be there, and we'll build a highway?" You know, it's like, it doesn't make sense. So I thought, but once you dig in, I think it really makes a lot of sense, all right? And it ties together a lot with what we've been talking about tonight, okay? The first is that the Earth's highway, right? I mean, this whole path that we're on started 4.5 billion years ago, right? And it's the Earth's highway, the path that Earth has taken, and in the process has created the situation where life can thrive, right? It's like the oxygen, you know, it goes all the way to the wild rice and the resources that we use all around us today. So it's part of that, the path I see is nature's path, okay? But it's also the human path, okay? The Native Americans that first came, then the miners, the loggers, the fishermen, the mariners, okay? Otto Rush, who we heard about last week, or 2 weeks ago, okay, came here and set up Washburn Iron Works, okay? And these people built the infrastructure that is now supports the lives that we have, okay? But then we also need to go to, so that's like the highway of a path leading to where we are today, okay? But the original meaning actually is from the Bible, and that is, a highway shall be there, and it shall be called the highway of loneliness, and the unclean shall not pass over it, okay? So this is like, you can also interpret this as like a higher way, right? And it's like, they'd say to me, my colleague said this, we think of this as the higher way, right? And it's like, that's what we're trying to do with our students. We're trying to like move forward in taking the higher path, okay? And one of the things about the past that has led us here is that we haven't always been respectful, right? In the way that that Native Americans were treated, in the way that the forest was cut down, the impacts of, the logging and the fishing, actually overfishing and some of the mining, okay? So it's like, not everything was done gracefully, right? But if we think about the lessons that we've had from the past, and this long and winding road that has led us to where we are today, and then we think about the path that we go forward, right? And let's take the honorable path, all right? And think about the past and honor the past and take the right path forward. Thank you.
Oh. Thanks a lot of this wonderful talk, and we're open for questions. I could think of a lot right now. Oh, there they go. Okay, and I'm going to bring the microphone because even if you think you have a loud voice, sometimes the people behind you, your voice goes that way. So, Ron, I'll start with you.
Question about when they had the oxygenation,
Yeah.
where did this oxygen, what was the source of that? Where did it come from?
Yeah, great question. Well, photosynthesis, right? So, well, the atmosphere was full of methane and carbon dioxide, right? It was a really very different atmosphere at that time. So it was actually kind of poisonous. So the first photosynthesizing organisms were like the pioneers, right? And they were turning it was the carbon dioxide, it was the oxygen in the carbon dioxide, right? And that's what photosynthesis does, it splits that, right? Yeah, it turns that into oxygen and plant material. Yeah. Yeah.
Bayview Beach has a reputation for having singing sand
Oh, yeah.
when you rub it between your hands.
Yeah.
Is there an geological explanation
Yes.
for that, or is that
Yes.
a farce?
Yeah, no, it is. And, well, it kind of depends upon how the moisture content as well. But yeah, the singing sands, what happens is that all of the quartz grains are pretty much the same size. It's what we call a well-sorted sand. They're the same size and they're old, so they're very well rounded, and they kind of roll over each other. So it's actually like, what you're hearing is when you do that, you press your foot down there and you push back, and it's like they're rolling over each other, right? And that happens. The same thing takes place in desert regions, where sand dunes that are well-sorted sand will actually become unstable, and they'll actually start to move down slope, and it's the same kind of process. And they'll actually, like, a pretty big avalanche can actually, the whole thing can start to vibrate, right? So we got singing sands on the beaches, and in the desert, some places there are booming sands for the same reason.
I like the singing ones better.
Yes, we talked about this just a little bit earlier here. Could you tell us a little bit about some of the new research that's been done in science, particularly about 6 months ago, with the idea that there might be hydrogen reserves, they're calling it geologic hydrogen, in the area here and around various places throughout the world that might be a real source of fuel that would be totally different from hydrocarbons.
Right, yeah, this is a big story. Thank you for bringing it up. It's a really big story. It's a news story. It was only about a year ago that the United States Geological Survey first published estimates of how much hydrogen, free hydrogen, there may be in the Earth. And the first estimates are much larger than anything that we had thought in the past in certain places. Okay, and the significance of this is that if there is free hydrogen, free meaning it's not bound to anything, it's not in water, okay? Which means that you could drill and you could take it out of the earth just as straight hydrogen, right? And it could be burned as a fuel, and what happens is the burning of it, it just reacts with oxygen in burning and you get water, okay? So there's no carbon, so it's not a carbon-based fuel. So this could be a really big story that we're just at the beginning of, all right? And it's created in certain kinds of rocks, all right, that we have a little bit of around here, not a lot, okay? These types of rocks are not that common. They're called serpentinites, right? And that's the kind of rock that is created in. So we'll see where this goes, all right? Does that answer your question? In terms of how much is here, there isn't a lot of rock that might contain hydrogen here, but there is some. So it's totally unexplored in this region. One thing I wanted to mention related to that is that this talk was about what we have here and the resources that have brought people here and supported us. What we don't have here is much energy. All right, and it's like all of this that we've been talking about has been supported by fossil fuels that have come from someplace else, right? First it came in as, well, first we burned wood, okay, but there's a lot more energy in coal, so the coal is coming in on ships, and then we had oil coming in, and now we have pipelines that bring natural gas in, right? So the story of energy around here is a really interesting one, and who knows where we're going? And so we know that we can't continue to burn fossil fuels at the rate that we do, right? So hydrogen may play an important role. The thing about hydrogen, though, it's pretty corrosive on pipes. So you could put hydrogen into the pipes, the existing pipes we have now, to about 1/3 of the gas that's coming into your house and burn it in the same furnace and everything. But you go to more than 1/3 and it starts to corrode pipes, right? Yeah, so we'll see where it's going. Thanks for the question.
Amazing questions, huh?
Yeah. Yeah.
About how much did the weight of the glacier depress the Earth's crust, and how long did the rebound take?
Yeah, okay, so the question is about how much did the weight of the ice depress the Earth's crust and how long it takes to come back. Okay, so ice depresses the Earth's surface about 1/3 the thickness of the ice. Okay, 1/4 to 1/3. So if it's a mile thick, it depressed it 1/4 mile, 1/4 or 1/3 mile, which is a lot. Okay, and the rebound takes place, it starts to take place, and it is the most rapid as the ice is leaving, and then so that this whole area has been rebounding. We're still rebounding, okay, we're still rebounding. It's slowed down a lot, but we're still coming up. Lake Superior, the whole basin has come up, and it's coming up fastest in the east. Okay, so this is what Lake Superior has been doing for quite some time. So actually, because of that, the lake is getting a little bit deeper at Duluth and shallower at the Sioux, right, because of the glacial rebound. Yeah.
And what's the approximate speed now? I mean, tenths of millimeters a decade?
Yeah,
or?
yeah, it's slow. I mean, it's yeah, but it's a measurable amount, right? It's like it is measurable, and it is getting deeper in Duluth. Yeah.
Are you sure?
Yeah.
We have a question back here.
Okay.
On the south and west sides of Eagle Island, there are these very long underwater fracture lines. And actually the east to the west one actually goes through the island.
It does.
So are those, especially the ones under the water, are those glacial striations, or are they something else that, and how did they develop?
Great question. Thank you. Actually, it was 2 summers ago, my buddy who does a lot of paddling out there, he said, "Tom, what the heck are these things?" Right? And he showed me his picture that he took out there, and he showed me the satellite image, and I was like, we gotta go. Right? So we did a little expedition out there, and so I studied them in as much detail as I could. And because I thought that if they are dikes of magma rock that came up through, you could date those, and it would be a very important date to understanding the geology of this region. And I thought, but how come nobody's dated them? Right? So I was a little bit skeptical of that, but then we went out there, and there are very distinctive cracks. Okay, it's all sandstone on the bottom there, very distinctive cracks. They probably are about 3 feet deep, and they're filled with rocks. Okay, so it's just a crack. They're 2 parallel cracks, okay, and actually they're big enough that, they're like this wide or this wide, like that. You can see them from a satellite image, and when the water's really clear, it's like 10 feet of water, you can see right down the bottom of it. Okay, but it is all sandstone. So they're just great big cracks. They're unusual, but they're not really anything that you couldn't explain just with the way the rock breaks apart.
That could become the
Right?
reflection of coming?
Yeah, okay, there is another aspect to it though, because the sandstone on either side of it is a little bit whiter color. So probably at the time that those cracks were forming, water was moving along those fractures enough to bleach the sand in that sandstone to be white. All right, so on the satellite image, you go there and you just, you can even see this on like Google Maps. Thanks for the question. Yeah.
You mentioned earlier in your
Yeah.
talk that Lake Superior was 300 some feet lower than it is
Yeah.
now. What caused the water level to rise again?
Yeah, all of that had to do with the glacial rebound, okay? Had to do with the way it's coming up, right? And I don't know the specifics, but the lake level, of course, has to do with the elevation of the outlet, right? And so the outlet has changed, and then, changed locations, and also the lake has been rebounding. So that's why, yeah. But 2,000 years is enough to make all these sea caves that we have.
And I don't know if we've got time for a few, maybe one or two more questions, and then if maybe Tom would stick around if someone
Sure.
has a
Yeah.
lingering question that we're not all, here we go, Tom.
Just east of, north of Highway 2 is a strip underneath the soil, way down just about a mile, where there's an oil field.
Oh, right.
When did that get formed and how did it get formed?
Yeah. So the Mid-Continent Rift had lakes in it. And some of those lakes had a lot of organic material. It's a billion years ago, so it was, pretty primitive life. But there is the old White Pine Mine in Michigan, not too far away, which is in some of those rocks where the copper is. We don't have the copper here, but they do in the same rocks going up the Keweenaw Peninsula. And the White Pine Mine had oil seeps in it. Okay, so these rocks underneath us did at one time have oil in them. And I understand that Exxon was very interested in this as a petroleum field. And my colleague Bruce Getz told me, Bruce retired, he taught at Northland College for 47 years and retired in 2016. He told me that it was 1983 that they were drilling right in that area. No?
92, 91.
91? Okay. And they drilled right in that area, and we don't know what they found, but evidently it was not enough to,
4,600 feet,
Whoa,
there was gas and oil.
okay,
I heard the grade wasn't the grade they wanted.
okay. I'll repeat that. You said 4,600 feet, there's gas and oil. Yeah. The sandstones here, they're mostly these red-brown sandstones, but in some places they have like the white spots, right? And the color bands in them, right? Those are created, they were all red originally because of the iron coating each one of the sand grains. And the iron has been redistributed, so dissolved out of the white places and then precipitated into the red bands. And I think, well, I don't know, but it's quite likely that those represent the passage of petroleum through these rocks, okay, a long time ago. So probably what happened is that there was petroleum in the Mid-Continent Rift, and a lot of it escaped to the surface through these sandstones and remobilized some of that iron on its way through. That's a really common thing. I mean, it takes special circumstances to actually trap oil into reservoirs. A lot of it escapes very slowly. There was one more we wanted to.
Yeah, there were some more questions,
Yeah.
and okay, we'll come back to you. And as I'm walking back, I want to thank everybody for being here again. Terrific topic and great audience participation, really wonderful.
Tom, as a geologist who studies these pristine lands and such, I'm wondering if you're concerned or if you're aware of Canadian concern that's got designs on opening up a copper mine in Porcupine Mountain. And they're really close to moving forward on it. And
Right.
Just
Yeah,
you worried about
Copperwood?
that?
Copperwood?
Correct.
Yeah, right. Yeah, wow. I don't know how far along they are in permitting. It's been a while since I heard much, but
It sounds like they're getting close to.
They're getting close?
Yeah.
Okay, yeah. Oh, yes, I am concerned about I mean, we need to take care of the environment, for the future. And, but we also need the resources, right? So it's like mining is such a difficult topic because, so many of our needs of society come together around mining, collide around mining. And the issues, when it gets sort of speaking generally, the issues come about when there's sulfur involved, which there is at Copperwood, they're copper sulfide minerals, right? And when there's sulfur involved and when there's a lot of water involved, because that's when you get acid and it can run off. So, I mean, yeah, there is reason to be concerned, right? And so we hope that the regulatory agencies are doing their job.
Well, I'm going to thank everyone at this point, and I thought of somebody when